pleasure to introduce Giacomo Zanella, who will talk about entropy contraction of the Gibbs sampler under log-concavity.
Okay, so thanks, Joris, and thanks to the organizers for the invitation. It's a pleasure to be here to present this work. So this is a joint work with Filippo Ascolani, who graduated last year at Bocconi and now is an assistant professor at Duke, and Hugo Lavenant, which is an assistant professor at Bocconi. Okay. Okay, so this is the plan of the talk, and please feel free to interrupt at any time with questions. There should be enough time. So the idea is, okay, I'll just set up the setting for sampling, and then I will go straight into the main result, which we'll present you, which is an entropy contraction result for the Gibbs sampler. After discussing the main implications, I will go a bit into the main idea of the proof techniques, and then I will discuss a bit comparison with optimization and gradient-based methods at a high level, and then finish with some extensions. Okay, so sampling, as we know, is the general task of generating random variables from a prescribed distribution. In this talk, I will be focusing on Euclidean spaces. So pi is a probability distribution on R to the D. Curly P denotes the set of probability distributions on such space. Typical motivation, for example, is say Bayesian modeling, but this talk will be general, in the flavor of this conference. And obviously, the challenge is where you have a high-dimensional target distribution. Okay, so RD when D is large. So I want to divide here to classify Markov-Chain Monte Carlo methods, which obviously are the kind of, it's well known that they are the main computational approach to perform sampling from general distributions. I want to divide them in two classes. Obviously, there would be other sort of classifications, which is the division into gradient-based methods, which are typically derived as discretization of stationary stochastic differential equation or gradient flows, like Langevin or Hamiltonian Monte Carlo-based methods, and methods which are more like of conditional updates or random projections, which typically work with coordinates. So the most well-known example is the Gibbs sampler in all its variants, like single site, blocked, and so on, Metropolis within Gibbs, and so on. Okay, and this talk, as obviously you can guess from the title, will focus on the second class of methods. Okay, so on coordinate-wise or random projection methods. Okay, so the whole of the talk will be focused on log-concave distribution, so providing non-asymptotic bounds under strong log-concavity assumptions. Okay, this is the context of this talk. So we'll assume that I have a potential U, which is a function from RD to R. I will make the classical assumption of the potential being M strongly convex and L smooth, meaning that if you have an Hessian, which you might not have, but assuming that you have an Hessian for simplicity, the Hessian is upper and lower bounded by constant multiples of the identity. Okay? I think most people here will be familiar with this kind of assumptions. It's the classical setup to provide non-asymptotic results, and is very much kind of an analog, if you want, of the more heavily developed convex optimization literature. And what I want to remark here is that it's a setting which is very heavily studied for gradient-based methods. There are still a lot of open questions, but there are a lot of results about gradient-based methods for this setting. And the starting point of this work is that despite the popularity in practice of the Gibbs sampler and related methods, especially for structured or hierarchical Bayesian models, among practitioners, there's really almost no result, no non-asymptotic result in the log-concave setting. Okay, so I'm happy then to discuss literature more in details, obviously. And so in some sense, the objective of this work was to try to provide some non-asymptotic convergence result of the Gibbs sampler under log-concavity. Okay, this is the objective of this work. Okay, so let's go straight into the main result. Okay, first of all, what is the version of the Gibbs sampler that we consider? What is the kernel that we consider? As I said before, let pi be a probability distribution on R to the D. I assume that it is partitioned into D coordinates. So in this slide, each coordinate, each block is one-dimensional. You can extend the result to multivariate cases where each coordinate is a multivariate object. For simplicity of notation in the slides, you can think at each xi as a real valued random variable. So you have a joint distribution on x1, xd, and the way you sample from it is just by updating it from the so-called full conditionals. Okay? So we consider the randomized version of the Gibbs sampler, which at each iteration you pick a coordinate at random. So you decide which coordinate to update, and you update it from its full conditional, so the conditional distribution of xi given x minus I. Okay? So if you are in R2, it just means that each iteration you choose either a horizontal or vertical line, and you update from the slice on the horizontal or vertical line. Okay? It's obvious to see that the resulting kernel is pi invariant because it's an average, it's a mixture of updating steps, each of which is pi invariant. And this is the kernel that we'll study in terms of convergence to stationarity. Okay? Okay, so we'll see the kernel as an operator in the space of measure. So it sends a measure from P over D to mu of P, which is the usual notation where mu P denotes the convolution. So it's the distribution of the Markov chain after one step, assuming that at the previous iteration it was distributed according to mu. And the main result that we prove is the following. So if you assume that you have a strongly convex and L-smooth potential, so you're in the setting of before, and you denote the condition number kappa as L over mu, then the Gibbs sampler operator is a contraction in KL, meaning that for any distribution in P over D, if you apply the Gibbs sampler, then the relative entropy with respect to the stationary distribution will decrease in a multiplicative fashion, and the contraction rate is uniformly bounded by 1 minus 1 over kappa D. Okay. So this, this is the main result, and the two interesting facts about the result is that it's uniform with respect to the starting distribution. Okay, so this is quite uncommon, unusual for Markov kernels. It's quite unusual to have contraction, especially for say discrete time Markov kernel. It's quite unusual to have a contraction in KL which is uniform with respect to the starting configuration. Okay, so this kernel, this theorem here requires no additional assumption beyond what is written here and holds for any distribution mu. Obviously, if you take a distribution mu which has an infinite relative entropy to pi, the statement is kind of vacuous. So you can say that it works for any distribution which has a finite relative entropy to pi, but then the coefficient is uniformly bounded with respect to mu. Okay, so that's the first feature. And the second feature is that there's no hidden constant, and the contraction rate is fully explicit in kappa and D, which are typically the main parameters of the problem. Okay. So this kind of contraction results have a lot of implications. Okay, there are many ways in which, as we all know, in which one could quantify the convergence to stationarity. This is one way to do it, and it's kind of a strong notion of convergence. For example, some things you could say is that obviously if you kind of just telescope it, you get a geometric convergence to stationarity in KL. And so this means that in terms of mixing time bound, if you want to have an epsilon distance to stationarity, the number of iterations you need to take, so the power n that you need to take, will be lower bounded by, let's say the mixing time will be upper bounded by kappa times d log of the starting distance minus log of the error. Okay. So here I'm just taking basically the original formula and I'm just inverting it. So what we see here is that the mixing time scales as kappa d, which is intuitive because it's kind of the 1 over 1 minus the contraction rate. So it's a way to turn the contraction rate into a mixing time. And the dependence both on the starting distance and on the error is logarithmic, which is kind of good. If you're worried about the starting configuration, the good thing of working with the relative entropy is that typically this scales polynomially with the dimension of the problem. So this really, for example, for M-worm distributions, this is a log m term. So there's no hidden polynomial term in the log of the starting distance because for so-called feasible starts, the starting KL, it's upper bounded basically by a linear term in D. So you should really think of this as a log D term. Okay? So if you ignore logarithmic terms in D and epsilon and kappa, then this means that you take order kappa D steps to converge to stationarity. Okay? So this is a statement in relative entropy. By standard functional inequalities, you get the same mixing time bound for, by say using Pinsker or Talleyrand inequalities, you get the same mixing time bounds for total variation or Wasserstein. Okay? So the tool that we use is very much related to the relative entropy, but the mixing time bound, you can kind of extend it to other sort of metrics. And finally, just in terms of the implication of the result, it's well known that entropy contraction for general Markov kernels, say pi-reversible Markov kernels, it implies a direct control on the spectral gap. So a corollary of the result is that the spectral gap is lower bounded by 1 over 2 times kappa d. Okay, so this is it's a strictly stronger result than a spectral gap bound. Okay, so in terms of what is the implication in terms of kind of computational cost of the algorithm? The key thing to notice is that we're studying the Gibbs sampler, which updates one coordinate per iteration. Okay, so we're picking randomly a coordinate to update, and we're updating it from the full conditional. Okay, so the computational cost of the algorithm will obviously depend on the model. Okay, but for most models, I would say for basically all models where the Gibbs sampler is used, The reason why it is used is that doing a conditional update is cheaper than doing a full gradient evaluation, and typically doing the conditional updates is of the same cost, the computational cost is of the same order as doing one full gradient evaluation. Okay? So for most models where this algorithm is used, basically doing the updates of the univariate Gibbs sampler has the same cost of evaluating the target or the gradient once. Okay? This is a bit, if you want to think at the optimization parallel, is a bit computing a partial derivative as opposed to the full gradient. If you have a model where computing partial derivatives is cheap, then it will be a model where using coordinate-wise updates will be potentially favorable. Okay? Obviously, again, this depends on the structure of the model, but it holds for, say, hierarchical models, generalized linear models, and so on. I would say it holds for any models where people do conditional updates. Okay? Otherwise, they wouldn't do it, I would say. Okay, so if you think of this as the unit computational cost, so the kind of unitary operation of computational cost, then you need to perform order kappa iterations of PGS to the D, okay, which is, I would say, what I would compare in terms of number of gradient evaluation. Okay, so it's an order kappa convergence result for strongly log-concave distributions. Okay, and it's quite remarkable that it does not depend on D, okay, in terms of computational cost. Okay, so here I'm not discussing implementation. First of all, because in practice, typically people use the Gibbs sampler because you have explicit full conditionals. If you have a generic log-concave distribution, you can use adaptive rejection sampling, which has a log kappa cost for each full conditional evaluation. Okay, so even theoretically, each step of the algorithm can be implemented exactly with no error at a log kappa cost. Okay, but although in practice, typically people use conditional conjugacy. And the key idea, obviously, is that each operation of the Gibbs sampler is just a univariate integral, if you want. So you're solving a univariate problem at a time, okay, not a multivariate one. Okay, so the main result, which I showed you, uses the kind of global condition number because this is the canonical quantity which measures the hardness of a distribution in log-concave sampling, but it's kind of well understood that it's not an accurate measure to characterize the speed of convergence of coordinate-wise methods because it doesn't really exploit the coordinate structure. Okay, so for example, it's well known that the Gibbs sampler is invariant with respect to rescaling of coordinates. If you stretch or compress or elongate a coordinate, then the Gibbs sampler operator is not changing. It's really the same algorithm, basically, with a different, represented in a different set of coordinates, while the condition number can change massively. Okay, so it doesn't really seize this kind of invariances. On the other hand, if you rotate a distribution, the condition number is invariant, while the Gibbs sampler could convergence, the dynamics of the Gibbs sampler could change massively. Okay, so these two quantities are not well correlated, and this is kind of well understood. Because again, one measures a sort of anisotropy, is rotation invariant, the other measures a sort of conditional dependence between variables. Okay. So the way people came up with better quantities in the optimization literature is to look at so-called kind of coordinate-wise condition numbers, where basically the first thing you do is you relax the joint smoothness to smoothness of one-dimensional functions. So you assume that your potential U is not jointly smooth, but is smooth only when you vary one coordinate at a time. So in terms of Hessian, it means that you are upper bounding only the diagonal terms of the Hessian, not the whole Hessian. So you assume that the ith term of the Hessian, the ith diagonal term of the Hessian is upper bounded by Li. And you assume that when you rescale coordinates according to Li, then you get a function which is jointly convex, and the convexity parameter, we call it 1 over kappa star. Okay. The reason to call it 1 over kappa star is that kappa star kind of relates to the condition number. Okay. So first of all, let's think at the intuition of what this assumption means. Well, the first assumption, basically, it's looking at the scale of the conditional distribution. So suppose that you have a kind of Gaussian-like target, then Li to the minus half is the conditional variance of the ith coordinate. And what you're doing is you are standardizing those to have conditional variance equal to 1, approximately equal to 1. Okay. This, in general, will be the lower bound to the conditional variance in the general case. And then once you standardize the distribution, you're looking at the largest, the direction with the largest variant. Okay? Which kind of makes sense that the longer this line, the harder for a coordinate-wise algorithm will be to travel the whole space. Okay? It kind of formalizes this intuition in the general log-concave setting. This is a strictly weaker assumption that strong convexity and smoothness, because if U is M convex and L smooth, then it always satisfies this condition with a kappa star which is strictly less than kappa. Okay, so it's kind of a generalization and a sharpening of the result because kappa star becomes smaller. And actually, a result which is the main result and the other is a corollary of this is that if you have this assumption, then the Gibbs anti-operator is a contraction with rate 1 minus 1 over kappa star d. Okay. So as I said, this implies the same result with 1 minus 1 over kappa d, but it's in general sharper because it takes into account of the structure of the coordinate-wise structure of the problem. In particular, why do I say that it is sharper? Because if you consider Gaussians, then this is almost an equality. In fact, people, there are well-known results for the Gibbs sampler on Gaussian distributions, okay, where you can compute exactly the kind of interesting quantities. So in particular, what is kappa star for a Gaussian? If you take u to be quadratic or pi to be a Gaussian, then the convergence of the Gibbs sampler depends on the correlation matrix between variables, on the conditional correlation matrix. So this means that you consider the matrix Cij, which is just Qij divided by square root of Qi, Iqjj. This is nothing but the conditional correlation of xi, xj given all the other variables. This is a correlation matrix. You invert it, you get a variance, and then kappa star is the largest direction, is the variance of the largest direction under this rescaled space. Okay, this is basically the plot I showed you before. Kappa star is really this quantity after you standardize the coordinates. Okay? And in the Gaussian case, what is known since work of Amit and Robert Sensau in the 90s is that you can compute exactly the gap in this case, thanks to the linearity of the problem. And the gap is exactly equal for any Gaussian distribution, is exactly equal to 1 over kappa star d. Okay? The spectral gap is connected to the entropy contraction for general Markov kernels, and this gives a lower bound to the entropy contraction coefficient of 1 minus 2 over kappa d. Okay? This is again exploiting general connections between entropy contraction and gap, and our bound is 1 minus 1 over kappa d, so there is a kind of room of a factor of 2, which is related to the fact that spectral gaps, that we use the spectral gap basically to get the lower bound, and indeed actually, in general, I think the contraction rate will be somewhere between 1 minus 1 over kappa star d, and 1 minus 2 over kappa star d. Okay. Although it's not easy to compute it exactly in general. What I want to highlight here is that I think in the log-concave setting is nice when you get results to see if they're tight for Gaussians, and in particular to see if they're tight for arbitrary Gaussians or only for special correlation structure. And the nice thing of the characterization to the kappa star is that this holds for any correlation type of dependence. Okay? It's not for some specific correlation structure, but it's for any Gaussian. Okay, so I mentioned already a few times the kind of connection with optimization, because indeed, if you're familiar with the kind of analysis of coordinate descent, there is a lot of elements which are kind of related to the analysis of coordinate descent in convex optimization. And indeed, there is a lot of connections between Gibbs sampling and coordinate descent. Suppose these are kind of two algorithms which try to do different tasks. One is trying to sampling from pi, the other is trying to optimize pi. But in terms of behavior, they have a lot of connections. And for a given pi, you can think at an algorithm which performs conditional updates. Every time you choose a coordinate at random and you update xi from its full conditional, or you can think at the corresponding algorithm which performs a conditional minimization of the potential given a randomly chosen coordinate. Okay? And obviously, this will converge, at least under convexity assumption, to the minimizer, and this will converge to a sample from pi. Okay. Another algorithm which I want to quickly mention, because it's kind of related, maybe people are already familiar with it, is the so-called coordinate ascent variational inference method. Indeed, there is, this kind of trio, if you want, sort of cousins, they are quite related. This is an algorithm which is slightly less obvious, but I think people in variational inference are very familiar to it. So here what you want to do is to compute the so-called mean field approximation of an arbitrary probability distribution, which is the best product form distribution which approximates pi in relative entropy. And one way to do it, also widely used in practice, is to go over to cycle or randomly choose factors and minimize the relative entropy for one factor at a time. Okay. So this is really a coordinate ascent or descent method in the space of factorized distributions. Okay. So the reason why I'm mentioning these three schemes is that all of these three schemes share the very same convergence rate in the strongly convex world. Okay. In the general is less clear, but at least in the strongly convex world, you have exactly the very same convergence rate. So here it's a bit of a heavy slide, but just the idea is to mention that all of them converge with the same rate, and this is tight for all of them for quadratic functions and is the best for general log-concave distributions. And the analysis of coordinate descent was well known since 2012, while the result for the coordinate ascent was proven first by Arnez and Lacker for the deterministic scan this year, and then we extended it to the random scan, where you can get sharper rates together with Hugo. And then the work I'm talking about is the work for Gibbs sampler. Okay, so these two, the second two are actually from this year. Okay. What I want to highlight here is that the first two methods, so the coordinate descent and CAVI, are really coordinate descent method which operate in a kind of Cartesian product space. Okay. Coordinate descent really uses the Cartesian product structure of R to the D and updates one variable at a time given the others. As I said before, CAVI really does the same kind of operation, working in the space of factorized distribution, but with objective function, the relative entropy. While what is, in some sense, a bit different about the Gibbs sampler is that it works in the space it operates in is the space of joint distributions of the variables, okay, which in general is much more rich and complicated than the space of product distributions of the variables, than, say, product of univariate distributions. Okay? So indeed, the Gibbs sampler is not in general a coordinate ascent method, it's more like a random projection method, as I will discuss. Okay, so any questions so far? Maybe I'll go a bit into the proof technique. Yeah?
Does the result for the Gibbs sampler imply the result for coordinate descent by setting the temperature to 0?
Okay, very good question. Okay, I never thought of it in this way. Let me think. I don't think so, but I don't know. I will think at it. I think they're kind of different, but I mean, even the proof is quite related. I will mention the differences. We didn't think at that point of view. Maybe there's yeah. I mean, I think it implies the one for coordinate descent when you send the temperature to 0, because Gibbs sampling in the limit becomes coordinate descent, like in an annealing fashion. I don't see a simple way to go from the Gibbs sampler to CAVI, but it's a very good point here. Maybe there was, yeah.
So the contraction rate depends on one d, and when the d is large, so the contraction rate is very close to 1.
Yes.
And for instance, the k and the kappa to get the small contraction rate.
So our perspective, the usual perspective, is that kappa and d are kind of given. And yeah, as you say, the contraction rate gets closer to 1, both as kappa and d increase, which is why the number of iterations goes linearly with kappa times d. So in general, we view kappa as fixed, so we don't kind of play with it. Although maybe by changing the parameterization, you can improve kappa star, but that's not like the perspective we don't examine that. But yeah. So in general.
So you talked about the going from kappa star by linear transformation. Of course, you do non-linear transformations as well, and you could make everything a lot more general, although obviously be less tractable. So the question would be, okay, this condition is you state it in terms of log-concavity, but really it seems to me it's a condition on dependent structure in the formula.
Yeah, it's a very good point. So it's true that we study an algorithm which does not depend. It really depends only if you want on the kind of sigma algebras, or I mean, if you do any bijective transformation of each coordinate, the algorithm doesn't change. While our technique uses the log-concavity structure, so you could think at optimizing the rate or the result over arbitrary transformations. Yeah, we haven't done it in general. I mean, you could obviously state it straight away that if you take any distribution pi and you can find any bijective map which is for individual coordinates such that the assumption is satisfied, then you get the very same contraction rate, because the KL is completely, I mean, this sequence of objects is completely invariant with respect to coordinate-wise transformations. But we haven't yet kind of played with it in examples or tried to find useful, if I understood your question.
Yeah, exactly. It feels like, to me, like it's really, if you look at the couplet when you transform
Yep.
everything, then it's really a tailed condition.
Yeah, you could state it like that, but then yeah, it should hold uniformly. I think you could state it like that. Yeah, definitely. It's a very good point. Yeah.
So I'm a little surprised in the similarity of the bounds. I think so. Maybe I understood something incorrectly. but in the coordinate descent, you're sort of wrapping over all coordinates. But in the Gibbs sampler, we're uniformly choosing one. Right? So I would expect another 1 by d.
So I was unclear, I think, in this slide. We are considering the same updating rule. So you should think at this tree paradigm with the same updating rule. So it was unclear. So for all algorithms, you sample I uniformly, and then you choose one of these three operations. Otherwise, obviously, they would be very different. And here I'm doing everything for random scan, just because it's a much nicer mathematical object. For deterministic scan, it's much more messy to study, and it's well known in the coordinate literature that the worst case is a factor of d larger, which is always a bit disturbing. If you do a full sweep of Gibbs in a cyclic way, in the worst case, you really don't improve over just choosing one randomly. But it's really, I would say it's really because the worst case and the average case are very different in the deterministic scan, but here everything is for the same random scan strategy. Yeah. I think it's more a theoretical, I see this more as a theoretical thing than practical, but currently the good bounds are only for the optimized version. Yeah. Okay, so maybe, okay, let's go a bit into the proof technique. Okay, so as I said, okay, the Gibbs sampler is just a mixture of kernels. Okay, so we have a kernel which is a mixture of conditional updating kernels. So you have an average of 1 over d sum over I of pi. Pi is the kernel which does a conditional update. So you keep x minus I fixed, you update xi from the so-called full conditional. So being an average of kernel just by Jensen, or if you want by convexity of the KL, you get that the entropy contraction will be bounded by the average of the entropy contractions. So the first step is just to use this upper bound. And here, what we need to control is the average of the decrease in relative entropy when we apply one of these kernels. Okay? So what do these kernels do? Well, these kernels are clearly projections, because if you apply them twice, it's like applying it once. And in particular, they are projections which are good, which is good to understand in terms of the chain rule of the KL. So what you're doing every time, you are decomposing the joint relative entropy into the marginal relative entropy plus the average of the conditional relative entropy. This is usually called the chain rule for the relative entropy. And what these kernels do, since they exactly set to the right full conditional, the distribution of xi, they basically kill the second term. So every time you apply a kernel pi, you are choosing one coordinate over which to do this decomposition, and you are removing the second term. Okay? So this gives the first chain of bounds, which is to say that the decrease in relative entropy when you apply the Gibbs sampler is upper bounded by the average of the relative entropy of the marginal distribution of mu of x minus I under mu relative to pi x minus I under pi. And this means that you can upper bound this quantity with any collection of d measures such that the marginal, removing the ith variable or of the ith element of my collection of measures, is equal to mu minus I. Okay? So this is to say that basically mu pi is the optimal distribution which preserves the marginal distribution. So you can choose the collection of nu I to try to find a tractable upper bound to this object. Okay? So the game of the proof is to try to find a good collection of measures mu I. And okay, the way you do it is convenient to use the kind of map terminology. Although here it's just, in some sense, I'm changing notation from before to here, but I'm not doing much more. I'm just writing out the nu i's as a push forward of mu under a map ti, which doesn't move all coordinates apart from the ith one. Okay? So you can think that you start from a general map, and then you define t, which goes from rd to rd, and then you define a collection of d univariate maps, which are the one that only move the ith coordinate, and you consider the push forward of mu under each of these maps. Okay, so you have a common measure, you push forward only through one of the coordinates. In general, the tricky bit is that if you're in the Euclidean space, then moving each coordinate at a time you just have a Cartesian product, while in the space of measures, you are pushing mu through kind of different push forwards, which are not, it's not clear if the result is coherent. Like to relate nu1, nu2, nu3 to the measure that you get if you push everything together, it's a bit like the technical aspect here. Okay? So we will try to find a map T such that you can control the average KL under this sort of univariate push forwards. Okay? So to control this quantity, it's good to decompose the relative entropy into the sum of potential energy and entropy. Okay, so that's a classical decomposition of the relative entropy. You just use the additivity of the log, and then you get these two terms. And what we will do is we will find a map such that we can separately control the two terms. Okay, so the inequality will apply to both terms, and thus will apply to the sum. Okay. Here, the first term, it's really just the average of the potential energy. So the proof is not that different from the proof that you get for coordinate descent, and then just taking an expectation over mu. So more or less, you find maps such that you can control the decrease in the potential function when you move one coordinate at a time, and then you take the expectation with respect to mu. So really, the first inequality, it's kind of a lifting of the inequality for coordinate descent. What is what is different, let's say, to deal with is the entropy part, okay? Because the entropy part really deals with the joint distribution mu, really deals with the fact that we are in a space of measures as opposed to being in the Euclidean space, okay? So the tricky bit is to control the average of the relative entropy if you move one coordinate at a time, and relate it to the relative entropy if you were moving everything together, okay? Sorry, not relative, to the entropy if you move everything together. Here the trick, in some sense, which simplified a lot, our job is to realize that triangular maps are a very nice object to try to control this kind of coordinate-wise push forwards, okay? So in particular, a triangular map is a map from RD to RD such that the ith coordinate of the map depends only on the first I coordinates of the input, okay? So if you want is a map such that the Jacobian, if you have a Jacobian, is a triangular matrix, okay? The nice feature of these maps is that it turns out that if you look at the average entropy, if you move only one coordinate at a time, it's always equal. Basically, this equality holds for any triangular map plus some regularity. It's always equal to the convex combination of applying basically all coordinates together, 1 over d times, and not applying any of them 1 minus 1 over d times, okay? This kind of equality does not hold in general, okay? So in general, for a general map T which is not triangular, this object can be larger than the object of the right, and it's not easy to quantify how large it is. Well, it's quite nice that for triangular maps, this is an equality, okay? The proof, in the regular case, in the smooth case, the proof is very simple because it's just about saying that basically the determinant of the Jacobian is the product of the diagonal terms, okay? So it really boils down from the triangular structure there. You can generalize it from, in a more measure theoretic way, using a lot of composition of the chain rule of the Kn, okay? But really, in the smooth case, the proof is easier. And this kind of motivates us to use triangular maps, as opposed, for example, to optimal transport map, which people typically use in this kind of literature. And eventually, the inequality, the final map that we use in the inequality is a convex combination between the identity and the so-called Knott-Rosenblatt map, which is nothing but a triangular map which pushes mu into pi, and it's coordinate-wise monotone. Okay, so this map, it's a classical object, is basically a conditionally optimal map on each full it's not on each full conditional, it's first on the marginal of x1, then on x2 given x1, x3 given x1 and x2, and so on. So if you take mu to be, say, the uniform distribution over the hypercube, then this map, it's really what implements the kind of inverse CDF method on the marginal, then on the conditional, and so on. Okay, so this is kind of a quite intuitive object. And then we need coordinate-wise monotonicity to basically be able to control the relative entropy along the path from mu to pi, along the linear path from mu to pi, which follows the Knott-Rosenblatt map. Okay? So in the end of the day, the proof is just to take this map and use this kind of inequality with this property to control, basically to get this desired inequality, and then you sum them. Okay? So I hope I conveyed the idea that the proof is quite direct in a sense. At the end of the day, the whole of the result is about proving this inequality, okay? Which in the literature, in the probabilistic literature, would be called an approximate tensorization of the entropy, because when pi is of product form, this inequality holds with kappa star equal to 1, and it's usually called the tensorization of the entropy. So in general, when people manage to prove these inequalities for distributions which are not of product form, they call it approximate tensorization of the entropy. And what we do is to prove this inequality for strongly log-concave distributions. Okay, that's at the end of the day, mathematically speaking, what we have to do. It's interesting that this inequality is strictly, in a very direct way, just by a linearization argument, it implies an inequality on the conditional variances, meaning that it gives a lower bound on the sum of the conditional variances of the full conditional distributions. Okay, so if you have x, which is distributed according to pi, and pi satisfies the assumptions I discussed before with kappa star, then the sum of the full conditional variances is lower bounded by 1/2 kappa star times the joint variance. Okay, so it's the decomposition of the joint variance over the one of full conditionals. Okay. And this is a strictly weaker result than the one above. Actually, we tried a lot to try to get this result directly before going to relative entropy techniques, and we couldn't find a way to do it. So it's kind of, for us, it's kind of open to try to get, I mean, this should be easier. So one might hope to try to get this with different techniques, but we couldn't get this kind of inequality if not by passing through the relative entropy. Okay, so the way we get this inequality for variances at the moment is passing through transport maps and relative entropy and then linearizing. Okay. This is probably a bit more intuitive, maybe if you're used to think. I mean, this is the Dirichlet form of the Gibbs sampler, and this is sort of the Poincare inequality for the Gibbs sampler, okay, for log-concave measures. This is more a log solid if you want type inequality. Okay, so in the remaining time, okay, so I'll discuss a bit comparison with optimization and gradient-based samplers. I already discussed a bit the comparison with optimization. Here, what I want to highlight is the difference between the coordinate-wise story and the gradient-based story, which is probably a bit more familiar in general to people. So in particular, what we said so far is that if you do coordinate-wise sampling and optimization for strongly log-concave distributions, you get exactly the same convergence rate, okay? And crucially, both of these say sequences exactly converge to the desired quantity. Okay, so the coordinate descent under strong convexity converges to the minimizer. The Gibbs sampler is exactly pi invariant. Okay, so it's not biased. So this means that really in this setting, I would say that there's no kind of gap between sampling and optimization because both schemes require the same number, so order kappa d conditional operations, which are either conditional sampling or conditional maximization, and they both converge exactly to the desired quantity. So really, even in practice, both in practice and in theory, there's no gap between the two in terms of polynomial orders and so on. Okay? I'm highlighting this because this is, I would say, quite different from what you get in the gradient-based context. Okay? Because in the gradient-based context, you have discretization error, which is very well known, to create a distinction, in some sense, between the rates of convergence of optimization and sampling. Okay? So here, for this audience, it's, sure, it's a bit basic probably, but I'm just mentioning this kind of phenomena for the simplest version, like gradient descent and unadjusted Langevin algorithm. It's well known that, say, if you take Wasserstein 2 and the function value for gradient descent, both schemes converge with the very same rate, the very same optimal rate, but gradient descent is unbiased, so it converges to the desired minimizer. So if you want the fixed point of gradient descent is the minimizer, the fixed point of the Langevin discretization is not pi. Okay, and then most of the game here is to try to quantify the error here. This error has a lot of different features, but in general, it always results in an error which goes, at least if you take worst case test function, it goes with dimension. And this means that at the end of the day, the number of gradient queries you need for an epsilon accurate sample grows with d. Okay, so for example, for ULA is order kappa d, while for gradient descent would be order kappa. Okay. Obviously, there are better methods than ULA, so you can reduce the polynomial here of d, but typically it's a positive polynomial. Okay. And here, again, what I want to highlight is that in the coordinate world, there's no, you can just avoid the discretization error because each operation is one-dimensional. Okay, so typically is implemented without discretization error. Okay, so it doesn't accumulate through coordinates. So this means that at least if you have cheap conditional updates, the Gibbs sampler converges with no order kappa joint evaluations. Okay, and this, I mean, here there's. I'm just putting some results for the competing methods, but probably there could be various different ones. I don't want to dwell much on this. Probably what I want to highlight is that if you believe at least the very best results for HMC, which basically are proven for Gaussians, say, then probably a practical message is that the Gibbs sampler has a better dependence with respect to dimensionality, but a worse dependence with respect to condition number, if you believe that HMC converges with the square root of the condition number. And I would say that in practice, this is typically what is observed, that if you have a very high dimensional model and you can find a good parameterization, then the Gibbs sampler can have a dimension-free convergence, while if you have a bad parameterization or a bad condition number, the Gibbs sampler pays the kind of ill conditioning in a more severe way than HMC. Okay, so here I'm putting some figure from a recent work by a group at UBC where they do a very systematic comparison of HMC and Gibbs. Here you sort of observe that, I mean, here also the condition number is increasing a bit because you are adding, actually you're adding, it's a kind of generalized linear model where they add dimension. But you see that typically the dependence with respect to dimensionality of the Gibbs sampler is blue is better than the dependence with dimensionality of HMC. So this kind of, I would say that this, especially these two predictions are quite, I mean, you do observe them in practice when you implement these methods. Okay?
Is there more to it than just the d to the 1/4, or what is at this distance here? How do you measure that?
So these are is just the,
I mean, asymptotically, you are claiming that one goes up and
Yes.
one goes, the rates are different.
yes.
Yeah, is this just the d to the 1/4 term, or is there more to it?
I think here it's a combination of d to the 1/4 and a slow growth of the condition number. They do a lot of simulation here and they kind of more or less get these numbers. Then, I mean, these bounds are typically a bit conservative, so I'm not sure how much, I think in this case, more or less they observe this, square root of kappa d to the 1/4 for HMC, and they observe order kappa for Gibbs. So obviously here I'm assuming that you can evaluate full conditionals. I mean, doing the full conditional evaluation is the same cost as doing one joint evaluation. Okay? Otherwise, obviously, this would be order kappa d, and you would not use conditional updates. Okay? At the end of the day, intrinsically, if you want, the fact that you can do cheap conditional updates is really at the heart of why the Gibbs sampler is good, because you can do small dimensional updates without introducing discretization error in a cheap way. So really, that assumption is quite crucial, I would say. So just to conclude with a couple of extensions, the general result, it's actually of this form where U is not the potential relative to the Lebesgue measure, but is the potential relative to an arbitrary product form log-concave distribution. If you want to say it in other words, you can assume any separable convex part to the potential. Okay? So really this reinforces the idea that U is a measure of deviation from independence as opposed to deviation from isotropy. This may be related also a bit to Garrett's question before. And this is also done usually in convex optimization for where coordinate descent is shown to be good with respect to non-smooth separable parts in the potential. And we have the same result for the Gibbs sampler. The second extension, this can be quite useful if you want to try to consider more realistic examples and modeling applications of this problem. The final example I want to mention is the extension or a corollary of the entropy contraction result for the hit and run. Because really, I insisted a lot on coordinate-wise methods, but really the key feature of our result is that you use random projections. And in particular, there is another very classical and famous method, which is the hit and run, which is widely used for, say, uniform sampling on convex bodies, is also quite studied theoretically extensively for log-concave sampling. Here we consider the log-concave sampling context. The idea is that rather than choosing the direction where to update from one of the coordinate axes, you just choose uniformly at random from the sphere. Okay? So you just choose at every iteration a direction uniformly at random from the sphere. You're at position X, you get a line, and then you do a conditional update from the line. Okay? This is again a mixture of pi invariant steps, so also the resulting kernel will be pi invariant, and it's known as the hit and run kernel. And here it's just basically one-line corollary of our result to show the same entropy contraction result for the hit and run, because really you can think of the hit and run as a Gibbs sampler of a randomly chosen axis. So if you think that you first randomize the axis and then you select one of them, you're really exactly implementing the same kernel.
It's exactly the same example. But it's exactly the same.
It's
no factor, it's exactly the same thing.
Yeah, I mean, the only thing is that you need to take the expectation. Here you would have a kappa star which depends on the axis, and you take the worst case. And then, No, again, it's exactly the same. So it's really, you just use the fact that the hit and run, you write it as a mixture of Gibbs sampler kernels, and then you use convexity of K. And and here I want to highlight that, again, there's no hidden constant, no additional assumption, so this is a quite sharp and nice explicit result for the hit and run. And the other thing is that this extends, I'm not putting in the slide, extends when you use L-dimensional hyperplanes, say. So if you, every time rather than choosing a line, you choose a L-dimensional space, here you get a contraction rate which is 1 minus L over kappa d. Okay, so you get a smooth improvement of the contraction rate if you just, rather than moving on a line, you move on a plane, on a three-dimensional space, and so on. Obviously, this is harder to implement, but it can have some interesting applications. So to conclude, we provide some sharp non-asymptotic results for the Gibbs sampler and more generally random projection methods under log-concavity in the sense of strong log-concavity and smoothness. We get the same convergence rate as optimization, but no bias. So we're quite happy to get the exact convergence rate for Gaussians and the same one as coordinate descent methods. If the model has cheap conditional updates, this means that in practice you would expect the Gibbs sampler to have an order kappa complexity in terms of joint target evaluations, which is basically somehow what we started from into proof. Things I didn't discuss, you can extend the result to metropolis within Gibbs by using comparison arguments, and you lose a constant factor which does not increase with dimension. And I already mentioned the extension to hit and run, and in the paper there's extension to the non-strongly convex case, and one nice application on the multivariate hit and run is an application to zero-order parallel sampling, which I'm happy to discuss afterwards if people are interested. And we're working on trying to build a bit more concrete examples to Bayesian models, which would be nice to have a bit of illustrations of this. Yeah. Thanks for listening.
We've had some questions already, but more.
Yeah, so if we, so since kappa star, whatever the choice of the coordinates, kappa star is larger or smaller, larger than kappa.
Yep.
If we look at your bounds, somehow we should never use hit and run because either we are lucky and we have good coordinates and kappa star is going to be less than kappa, or we are not lucky and kappa star is kappa and we just get the same bound with Gibbs sampler than with randomly choosing the coordinates.
So the bound I showed here is just the worst case, just using an upper. So the bound, you could get a sharper bound where here you have expectation of 1 over kappa star for randomly chosen axis. So I think the message is not that this is always worse than Gibbs. It's just a bit telling you the obvious thing that if the original coordinates were better than averagely chosen one, you should go with that. Otherwise, this is picking the average case. Whether the average case is close to the worst one, I don't know. We would like to study, but I mean, yeah, it would be nicer to get something a bit sharper here because I could say that this is not sharp for hit and run in the same way as the original result was not sharp for Gibbs. So I wouldn't say that it allows to compare the two in some sense. The real issue with hit and run is that you don't get for most models, you don't get the cheaper conditional updates. So I think people in practice use this less because it has the same cost of a full target evaluation. So then it's more similar if you want to a random walk method. So really that's, I think, is where the big difference is.
I think Gareth had a question.
Yeah, so you talk about connectionistic additional maximization. But so the obvious question would be about the EM algorithm and various versions of that. Have you thought about that?
Yeah, I don't know. I don't think. Yeah, there is a lot of connections also in the literature from the 90s about the convergence rate between those. We didn't explore this extensively. I think there are also recent works on that, but yeah, I think in the EM you would have a bit of a latent structure. I mean, the type maybe you have more structure in the problem, so you should exactly define how you do the parallel. But I think probably there are a lot of parallels that could be done. But yeah, we haven't looked at it definitely. Yeah, thanks.
Since final question, Alex.
Yes. So I have the impression that so you have a number of steps. You have this kappa that does not increase with dimension, right? So your results.
I mean, our results apply as common in this literature. You fix D, you fix kappa, and you get the bound. Then, yeah, depending on which asymptotic regime you consider, kappa will increase with dimension or not.
Yes. So in some cases, it's not that surprising, right? Because you are doing a Gibbs sampler, and apparently, if you had IID, for instance, components, that wouldn't be surprising at all. And somehow you control the dependency through your system.
Yeah, I agree. I mean, whether it's surprising or not, I think it depends. But I mean, yeah, I mean, I guess what he's saying is that, I mean, the fact that if you fix kappa in the sense of the classical log-concave, well, yeah, I don't. Yeah, it makes. I agree. It's in accordance with intuition. Then whether this is the right quantity or whether you have a higher powers of D or kappa, I guess is not obvious a priori.
Yeah,
but,
you can have models where as you increase the correlation increases, for instance, components. In that case, there would be some issue.
Definitely, yeah. So definitely, when you apply this to a practical model, you should study how kappa scales with D to get conclusions. I completely agree with you. Yeah, definitely.
All right, so let's thank Giacomo again.